Welcome back to the Deep Dive. Our mission today is all about the real-world gravity of machine learning.
That's right.
We are leaving the insulated environment of the research lab, putting down the academic papers, and we're diving headfirst into the brutal, fascinating reality of production ML systems design.
I think brutal is the right word sometimes.
It can be. So this deep dive is really your blueprint for understanding what it actually takes for that perfectly tuned algorithm to survive and thrive when it's interacting with millions of real users, real data, and, real business requirements.
Precisely. And if you're coming from a background of pure model development, maybe you're great at tuning hyperparameters or inventing new architectures, this is the essential next step.
Right.
We're moving beyond the model itself, and we're tackling the holistic view.
Okay.
We have to understand the entire ecosystem. What we're covering today is essentially the strategic design framework for modern MLOps.
Right.
It's all about ensuring that the entire pipeline, from the moment you capture the data to the moment a user gets a prediction, is robust, reliable, and actually delivers business value.
Okay, so let's unpack that concept of the holistic approach, because it sounds like what you're saying is the algorithm is maybe the easiest part, and everything else around it is the real engineering challenge.
That is often the case, yes. The model is typically just a small piece of the puzzle. I mean, the fundamental challenge of ML systems design is that these systems are inherently complex and they are highly unique.
Complex and unique. How so?
Well, they're complex because they consist of so many moving parts.
Yeah.
You've got the data ingestion stack, maybe a feature store, all the cloud infrastructure, the deployment mechanism, the monitoring dashboards. It's a lot.
It's a whole system of systems.
It really is, and they're unique because, unlike traditional software, they are profoundly data dependent. What works for one company's dataset might fail completely for another, even if the business problem seems, identical on the surface.
And the complexity doesn't just come from the technology, does it? The source material makes it really clear that the people involved, the stakeholders, they add a whole other layer of friction.
Absolutely. Traditional software often has clear functional requirements. With ML systems, you have these inherent, often conflicting objectives.
For example?
Well, the data science team is, laser focused on model accuracy and predictive performance. F1 score, AUC, that's their world. But the engineering team, they prioritize low latency and system reliability.
Uptime. Speed.
Exactly. And then the business team comes in and they care most about interpretability, understanding why a prediction was made, and ensuring the system is maintainable for long-term cost efficiency. You simply cannot maximize all of those things at the same time.
So there's always a trade-off.
Always. That tension is just baked into the design process.
So if we define machine learning systems design as this process of making sure all these components and all those conflicting stakeholders work together to satisfy a unified set of business objectives.
Yeah.
How do we even start to structure that chaos? It can't be a clean, linear software development path.
No, absolutely not, because the data is dynamic, and the real world changes way faster than any textbook process allows. We have to embrace the iterative nature of the work.
The loop.
The loop. The source material outlines the ML lifecycle not as a straight line, but as a continuous cyclical process. This is the foundation of the MLOps philosophy. Continuous everything.
Okay, so let's walk through that loop. It's a 6-phase system, and it starts, maybe counterintuitively, far before any data scientist opens up a Jupyter notebook.
Right, it has to. It starts with project scoping. This is the most crucial, and I'd say often the most rushed phase of the whole thing.
And what's happening here?
You're defining the actual business problem, not the technical problem. What is the measurable value this prediction is going to deliver? Are we trying to increase click-through rates, reduce inventory churn, or improve user satisfaction? You also have to determine if machine learning is truly the necessary and cost-effective solution in the first place.
I think that last part is so important. It's where a lot of enthusiasm needs to be tempered with a dose of reality.
It really does. Look, ML excels at learning complex, constantly changing patterns from existing data to make cheap, approximate predictions on new data. But if the rule is simple and stable, say, if the temperature is over 90 degrees, send an alert. A simple, hard-coded software solution is always, always preferable.
Because ML introduces a ton of complexity and maintenance overhead.
Exactly. And it only justifies itself if the underlying patterns are truly opaque or constantly evolving.
Okay, so once that decision is made, we pivot immediately into the technical foundation, which is data engineering.
This is the massive, invisible iceberg supporting the tiny tip of the model. This phase is all about building robust, reliable data pipelines. It's about cleaning, structuring, and moving vast amounts of raw data efficiently.
So this is where we're building the infrastructure, the data lakes, the relational databases, the streaming services.
All of it. And executing that crucial ETL process. Extract, transform, load. I can't overstate this. This phase determines the absolute maximum performance ceiling of your eventual model. Bad data means certain failure.
And crucially, this phase often loops right back to the scoping phase. I mean, if during data engineering you discover the high-quality data you need just doesn't exist or it's way too expensive to collect.
The project scope has to change immediately. That's that continuous feedback loop in action. But let's assume the data foundation is solid. Then we finally move to ML model development, which is the part everyone tends to focus on.
Right, this is where we see the traditional data science tasks. Feature engineering, picking the right algorithm, hyperparameter tuning, and all that rigorous offline evaluation using metrics like AUC or F1 scores.
Exactly, but in a production context, this phase is way more constrained than it is in academic research. Here, the team has to incorporate all those diverse production requirements we just mentioned.
Like latency.
Like latency. A researcher might only care about raw accuracy, but a production engineer needs the model to run fast. So the architecture you choose has to meet strict latency budgets. If your amazing, super accurate model takes 500 milliseconds to deliver a prediction, but your service level agreement demands 50 milliseconds,
it's useless.
It's completely useless. So this phase forces these really complex trade-offs between pure performance and operational speed.
And that sets us up for the moment of truth. Deployment. This is where the model is pushed into the environment where real users are actually interacting with it.
Yep. And deployment introduces architectural decisions that have profound consequences for the rest of the system. We have to decide between batch prediction and online prediction.
Could you break that down for us?
Sure. Batch prediction is simpler. Think about calculating movie recommendations once a night, or running a large financial risk assessment overnight. Latency doesn't matter much there.
You just run it on a schedule.
You run it on a schedule. But online prediction demands real-time responsiveness, like predicting the next word as you type, or instant fraud detection. This requires robust API endpoints, constant availability, and introduces massive complexity and those strict latency demands that fundamentally change the entire infrastructure setup.
And once all that complexity is live, the work is, I imagine, nowhere near done, which leads us into the critical ongoing phase, monitoring and continual learning.
This is non-negotiable for survival. The production world is dynamic. Your model's input data is not static. It is constantly shifting.
Things change.
Things change. So we have to monitor for data distribution shifts. That's where the live data the model sees starts looking significantly different from the training data it was built on. When your feature values shift, the model's performance degrades. We call that model drift.
And monitoring also watches for just, basic software system failures and the integrity of the features and the labels themselves.
Exactly, and the continual learning part.
That's how you fix the drift.
That's how you address the drift. It ensures the model can be frequently, or maybe incrementally, retrained using new live production data to maintain its performance over time. And this requires an automated retraining pipeline, which ties directly back into the data engineering phase, creating that true circle.
Which finally loops us all the way back to the ultimate measure of success, business analysis.
This is what closes the loop. It answers the question we posed all the way back in the scoping phase. We measure the actual real-world impact of the deployed model against those initial business objectives.
So, did our recommender system's tiny 0.2% accuracy bump actually translate into the millions of dollars in revenue we projected?
Or was the added computational complexity of that bigger model just entirely unjustified? The findings here, the ROI, the customer satisfaction scores, the operating costs, they feed directly back into project scoping for the next iteration. Maybe it requires a complete pivot in technology or strategy.
That structural definition of the life cycle is really important, but I think the visual of those dashed lines connecting the phases in the source material is the key lesson. It's not a neat circle.
It is not.
If monitoring reveals, say, unacceptable latency or massive model drift, the team might have to jump directly back from monitoring to model development or even data engineering, bypassing other steps.
That flexibility is paramount. Production ML is fundamentally iterative, not waterfall. A change in the deployment architecture, like switching from a CPU to a dedicated edge device, will inevitably affect the model development phase. It's going to force a reconsideration of model size and complexity. If the system is not designed holistically, those feedback loops break down, and the whole thing just collapses into an unmaintainable tangle of duct tape and manual checks.
So the iterative lifecycle defines how we build these systems, but the success of the system is ultimately judged by how well it adheres to four non-functional requirements. Let's set the bar here. Successful production systems have to be reliable, scalable, maintainable, and adaptable.
These four requirements, reliability, scalability, maintainability, and adaptability, or RSMA for short, are where the real engineering talent is required. A brilliant model is completely useless if the system supporting it is unreliable. Let's start with scalability, because that is the requirement that immediately separates a student project from an enterprise system. It addresses how well the system can handle increased demand and growth in data or user load.
When most people think about scaling, they probably imagine traffic increasing and they just need a bigger computer. But the source material makes a really important distinction between how that growth actually happens.
Yes. There are two distinct methods for scaling your resources. First, you have scaling up, which is also known as vertical scaling.
Okay.
This means making a single component larger or faster, like upgrading a database server with a much larger CPU, more memory, or a faster network card. It's often simpler to manage at first, but it hits very hard limits very quickly.
And then there's the standard cloud approach, which is scaling out.
That is scaling out, or horizontal scaling. This involves adding more parallel equivalent components to spread the load. So instead of upgrading one massive server, you add 10 identical virtual machines behind a load balancer.
Which is more complex to manage.
Much more complex to orchestrate because you have to manage distributed state and consistency, but its potential for growth is, virtually limitless. A production ML system, by necessity, must be capable of scaling out to handle user load.
And the complexity of resource scaling is tied directly to managing cloud costs, isn't it? It requires dynamic adjustment, not just growth. You need the ability to shrink when demand drops.
This is absolutely critical for cost efficiency. We talk about needing both upscaling and downscaling. Consider a global fraud detection model.
Okay.
At peak times, maybe during major global shopping events or a specific financial window, it might genuinely require 100 dedicated GPUs to process real-time requests without any latency spikes. But for 80% of the day, it might only need 10.
And if you're paying for those 100 GPUs 2, 4 to 7,
your cost will be crippling. So the system has to automatically detect the reduction in load and deprovision those 90 excess GPUs, or maybe move them onto cheaper, preemptible instances.
This is all managed by something called auto-scaling.
Exactly. And it's indispensable, but implementing it is one of the trickiest operational challenges in cloud infrastructure because it often involves predicting future load and managing cold starts. That's the delay involved in spinning up a brand new resource from scratch.
And we have a phenomenal real-world anecdote that just demonstrates the terrifying cost of getting auto-scaling wrong, even for the most sophisticated players in the game.
The quintessential cautionary tale is Amazon's Prime Day crash. This happened years ago, but the lesson is absolutely timeless.
What happened?
Well, on a day of massive predictable demand, Amazon's own indispensable feature, their own auto-scaling mechanism, failed. The system just couldn't adjust quickly or robustly enough to the unprecedented surge in traffic. Instead of scaling out seamlessly, the internal system got overwhelmed, which led to cascading failures across the site.
And the consequences were staggering.
That single hour of downtime resulted in estimated losses between $72 million and $99 million in lost sales.
In 1 hour?
In 1 hour. This hammers home the point that the failure point isn't usually the algorithm missing a prediction, it's the operational infrastructure failing to meet the demand. This is why reliability, designing a system that's robust against failures, and adaptability, the ability to handle new requirements, are so crucial. If your infrastructure isn't adaptable, that $72 million mistake becomes a very real possibility.
Okay, so we've covered scaling resources, but scalability isn't just about hardware. We need to talk about the deeper architectural challenge of scaling the models themselves. That shift from managing one prototype to managing hundreds of models, maybe for different regions or customers or use cases.
This is the realm of artifact management, and it's a total paradigm shift. I mean, when you have one proof of concept model, version control is simple. You save the code, maybe you note the hyperparameters in a text file, and you call it a day.
Right.
But imagine a scenario where you have 100 different models running simultaneously, maybe 50 recommendation models personalized for various user segments, 30 fraud detection models for different payment methods, and 20 forecasting models.
Manual monitoring and manual retraining become instantly infeasible.
Completely infeasible. Scaling out models means you have to treat the model itself and all the data that created it as a traceable, managed artifact. You need a robust system to manage code generation, track versions of the specific data slice used for training, the exact feature schema, the configuration parameters, and the final serialized model object.
And this is often handled by a centralized system, right? A model registry.
Yes, a model registry. It sounds like version control for the entire ML pipeline, not just the code.
That's an excellent way to put it. The model registry tracks all of that metadata. So if model 73 suddenly starts showing performance degradation, say the click-through rate drops by 5%, the registry allows you to instantly pull up the exact code version, the precise feature store schema, and the configuration that created the working version of model 73 6 months ago. Without that, you're lost.
Without this rigor, debugging a failure in a portfolio of 100 models becomes a 6-week archaeological expedition. It's a nightmare.
This complexity is why we move beyond just continuous integration and continuous delivery, CI/CD, from traditional software to continuous training, CT, and MLOps.
Absolutely. CI/CD for ML demands that you can automatically rerun your entire training pipeline, including feature engineering and validation, in an automated, reproducible way whenever new data arrives or performance degradation is detected. This CT pillar is completely reliant on robust artifact management, ensuring you are building the right model from the right ingredients every single time, often many times a day. This rigorous system of systems, from data collection to artifact management, is what truly defines production-ready scalability.
That sets the stage perfectly for the core component underlying all of this complexity.
All right.
The data. And it's hard to talk about this field without addressing the core philosophical debate shaping research right now, this whole mind versus data discussion.
It's truly fascinating because it's a reframing of a decades-old argument in AI. Do we prioritize intelligent design, or do we prioritize sheer computational brute force? This debate gives rise to the powerful data overmind camp.
And the most cited and perhaps most provocative idea here is Professor Richard Sutton's bitter lesson.
The bitter lesson is, it's essentially a cautionary tale drawn from 70 years of AI research. Sutton argues that whenever researchers achieve a short-term, impactful result by leveraging their human domain knowledge, what he calls the mind approach, like clever hand-engineered features or specific rules, that approach is always eventually surpassed by general methods that simply leverage immense computation and large data sets.
So the core thesis is that general, computationally intensive learning methods are ultimately the most effective by a large margin, and relying on human intuition for specific domain knowledge is basically a long-term distraction.
That's the core argument. The human mind is great at providing quick, initial improvements. For example, knowing that a customer's address history is a vital feature in a fraud model, that's human mind. But according to the bitter lesson, if you build a massive, generalized neural network and you feed it petabytes of raw, unstructured transaction data with immense computational power, it will eventually discover more complex, nuanced, and effective patterns that no human could have conceived of or manually engineered.
That sounds like a license to just throw infinite compute at everything.
Yeah.
If I'm a startup with limited resources, is there a point where the mind approach, clever feature engineering, smart, small data techniques, still wins? Does the bitter lesson hold true when the data and compute budget is finite?
And that's the critical, practical question, and it's where all the nuance lies. Sutton's argument focuses on achieving ultimate state-of-the-art generalization. For a small company solving a niche problem, the human mind approach, that clever feature engineering specific to their domain, is often faster, cheaper, and entirely sufficient.
So the debate is about the end game.
Exactly. The debate centers on whether finite data is enough to achieve human-level intelligence, not whether data is necessary at all. But when you look at the trends for maximum performance, the trend is just. It's undeniable. Computation and data rule the day.
The source material drives this point home by showing the exponential, almost frightening growth trends in language model datasets. The reliance on quantity is just stark.
We have to appreciate the scale of this growth and how rapidly it accelerated. I mean, look back to 2013. The academic standard for language modeling was the 1 billion word benchmark. It used about 0.8 billion tokens of text. That felt absolutely massive at the time.
And just 6 years later, the scale had already exploded.
By 2019, with the release of OpenAI's GPT-2, the dataset size jumped more than tenfold to 10 billion tokens. Researchers just needed more and more raw material to push the boundaries of performance.
And then the acceleration went vertical.
In just one more year, 2020, with the introduction of GPT-3, The training dataset size ballooned to a staggering 500 billion tokens. This exponential growth, it illustrates a simple practical reality. For now, the path to groundbreaking performance is paved with orders of magnitude more data, demanding specialized hardware and immense computational resources just to train a model one time.
It validates the bitter lesson in practice.
It does, even if the philosophy is still debated.
But sheer quantity is such a dangerous metric if we ignore quality. And this is the crucial caveat that brings us right back to the earlier phases of the ML lifecycle.
It is the single most important practical caveat for anyone designing an ML system. More data does not always lead to better performance. Low-quality data that is outdated, noisy, potentially biased, or critically, data with incorrect or ambiguous labels can actively hurt your model's performance, stability, and its ability to generalize.
Garbage in, garbage out.
Garbage in, garbage out, scaled to the terabyte level. The quality of your data dictates the absolute ceiling of your model's performance, regardless of how complex your algorithm is or how much compute you throw at it.
This inherent dependency on robust, high-quality data is best visualized by something the source brings up. Monica Rogati's AI hierarchy of needs, which just flips the perceived importance of algorithm development completely on its head.
This hierarchy is such a critical conceptual tool. It shows us that most of the effort, most of the investment, and most of the infrastructure must be dedicated to the data stack, ensuring that the necessary quality and quantity exists before we ever reach that glamorous top layer of deep learning.
It's a pyramid.
It's a pyramid, and most of the structure is dedicated entirely to stable data engineering and flow.
Let's dedicate some serious time to describing the stack from the bottom up, layer by layer, because it really shows the heavy engineering lift required at the foundation. The absolute base is the collect layer.
This is the essential foundation, the instrumentation layer. It involves setting up reliable logging, integrating sensors, configuring telemetry from applications, and capturing both external data sets and user-generated content.
So if your ability to capture data is unreliable, if your logs are dropping 10% of events, or your sensors are failing randomly, you're basically building on a fault line.
You are. You need to ensure you are collecting the right raw data in a consistent format across all your operating environments. And this involves making critical architecture decisions right out of the gate about data granularity and event structure.
Okay, moving up one layer.
Yeah.
Once the data is collected, it needs to be managed efficiently. This is the move store layer.
This is all about infrastructure and reliable data flow. This layer is responsible for creating data pipelines that can handle massive throughput. This involves modern, scalable storage solutions, think technologies like S3 buckets, data lakes for unstructured data, and high-performance relational or NoSQL databases. It also encompasses the physical transportation of the data through ETL, or increasingly common ELT pipelines.
Can you specify what the transform in ETL means in this context? We're not at the modeling phase yet.
Certainly. In the move store phase, the transformation is usually about structural cleaning and normalization. It means moving data from its raw, collected format into a more structured format that's suitable for querying and aggregation. For instance, converting multiple timestamp formats into a single, canonical format, or joining disparate log streams based on a consistent user ID. It's making the data usable and queryable for the next stage.
And that leads us to the third layer up, explore transform. This seems to be where the data team starts actively preparing the data for the modeler.
This is where the deep cleansing and preparation happens. This is the domain of handling the messiness of the real world. You are actively performing anomaly detection, using techniques like isolation forests or robust statistical checks to identify and handle egregious outliers or corrupted records.
And handling missing values.
Yes. Dealing with missing values through imputation, correcting obvious structural errors, and performing tasks like noise reduction or standardization. If the data is too messy at this stage, the eventual feature engineering effort becomes a complete nightmare.
Next up, we hit aggregate label. Now we're generating the artifacts that will directly feed the model.
Exactly. This layer focuses on two key tasks. First is aggregation. Calculating analytics, defining core business metrics, and crucially, creating the features themselves.
Okay, what's a feature in this context?
Features are the aggregated, cleaned, and derived signals that the model uses for prediction. This is where you might calculate the 7-day rolling average of user logins or the ratio of failed transactions in the last hour. And second, you have to generate the labeled training data required for supervised learning. This process, often requiring human annotation and rigorous quality control, is absolutely essential.
Because without high-quality, accurate labels, even the best features are totally useless.
Really useless.
We've spent most of our time in the bottom 4 layers. Now we finally reach the layers that traditionally get the most attention. Layer 5 is Learn Optimize.
This is the first level where algorithms really take center stage. This layer is dedicated to experimentation, A/B testing of hypotheses, and establishing solid baselines. We typically use simpler, more interpretable machine learning algorithms here, things like linear models, decision trees, to validate the features and the data quality.
And these simpler models serve as the benchmark.
Exactly. They are the benchmark against which the complex models at the peak must prove their worth. If a simple linear regression model performs 90% as well as your massive neural network, you often just default to the simpler model because of its maintainability and speed.
Which brings us, finally, to the tiny, tiny peak of this massive pyramid, a deep learning.
This is where the complex, resource-hungry, state-of-the-art models live, the massive language models, the sophisticated image recognition networks. The visual synthesis of this hierarchy is stunning. All the complexity, all the algorithms, and all the research that grabs the headlines at the top rely entirely on the foundational layers beneath.
So the infrastructure is shaky at the collect layer.
Or if the transformation is inconsistent at the explore-transform layer, or if the features are stale in the aggregate label layer, the deep learning model at the peak will collapse the second it hits production reality.
What's fascinating about this hierarchy is the insight it gives you into resource allocation. I mean, for engineering teams accustomed to traditional software, they often overinvest in that learn optimize layer because that's the intellectually stimulating part. They completely underestimate the scale and complexity of those bottom layers.
That underestimation is the greatest risk in modern ML systems design. The majority of the maintenance effort, the majority of the budget, and the majority of the risk are all concentrated in those lower layers. We are, in essence, building massive data management systems that just happen to have a small predictive algorithm bolted onto the top.
Right.
And that realization ties directly back to our discussion of production requirements. This system is complex precisely because we are building this robust data hierarchy to ensure reliability and scalability.
That seems like a perfect place to synthesize these foundational lessons from the Introduction to ML Systems Design. We started by defining the mission. This mandatory shift from siloed, algorithm-focused modeling to a holistic, iterative, systems engineering perspective that constantly loops back on itself for refinement.
And we detailed the necessary architectural shift that's required to handle the real world. This includes solving those non-functional requirements, reliability, and particularly the two faces of scalability. We showed that scalability means not just buying more powerful hardware, but managing resources dynamically through auto-scaling and managing the increasing complexity of model portfolios through rigorous artifact management and model registries.
And then beneath all that infrastructure, we found the philosophical and practical truth about data. We explored the bitter lesson, debate mind versus data, and we concluded that while the philosophy is complex, the practical reality in the pursuit of state-of-the-art is currently driven by massive, exponentially growing data sets.
And then we use the AI hierarchy of needs to drive home the structural point that robust data engineering isn't just a prerequisite, it is the actual foundation supporting the entire system.
So what does this all mean for you, the practitioner, the engineer, the designer?
The defining realization from this deep dive is that modern ML systems are inherently complex systems of systems. They consist of many deeply interconnected components. The data stack, the deployment infrastructure, continual monitoring, maintenance protocols. I mean, if you're entering this field, focusing only on the ML algorithms is nowhere near sufficient. You have to be a systems thinker.
The system approach we've outlined here, holistically, considering all requirements, from business objectives and interpretability demands, all the way to low latency constraints and scalability thresholds, is the defining feature that truly distinguishes production-ready ML from a pure academic or research project.
Absolutely. And this realization leads us to a final provocative thought for you to consider as you move forward with your own systems design.
Yeah.
We established that sometimes achieving a marginal improvement in model performance might not even be noticeable to the end user, which often justifies the choice of a simpler, faster, more maintainable model. Conversely, we learned that achieving that extra 1% of state-of-the-art accuracy often requires leveraging an exponentially increasing amount of computation and data.
So given your limited time, your limited budget, and your operational constraints, how do you determine the acceptable trade-off point? Is that marginal performance gain from deploying a massive, complex, state-of-the-art model, say, gaining 1% accuracy, truly worth the resulting complexity and all the accompanying non-functional risks?
Risks like moving from a system that delivers a prediction in 50 milliseconds to one that requires 500 milliseconds, coupled with greater instability, increased development time, and 10 times the operational cost.
Where do you draw that line?
That is the core trade-off decision you will face every single day in production MLOps. Where do you draw the line between algorithmic performance and operational robustness?
A fantastic question to leave you with, because production ML is, in the end, the study of trade-offs. Thank you for joining us for the deep dive today.
Until next time.